Hi everyone and welcome to the channel. Today we're going to be discussing what I consider to be fundamental vector knowledge going into a physics classroom at university for the first time. Now obviously I'm not going to cover everything about vectors in one video without it being mind-numbingly boring. However, I am going to attempt to give you an essential overview of everything you will fundamentally need, what I view to be the vital beginner knowledge for starting an undergraduate physics course. So let's get started. In this video, we're going to go through 5 key points, starting with reminding ourselves of what exactly a vector is, before discussing the notation used to represent them. After this, we'll turn to look at basic vector operations, a few differentiating concepts, and then finally tying it all together by learning how to differentiate the vector operations themselves. So starting at the fundamentals, we have to ask ourselves, what is a vector? Well, simply put, a vector is a quantity with both magnitude and direction. The most obvious example of a vector is the position vector, which gives the position of an object from some origin and in some coordinate system of your choosing. In this case, we'll describe it in Cartesian coordinates, which are the usual x and y axis in 2 dimensions, or x, y and z axis in 3 dimensions. The distance the object is from the centre is given by the length of the vector, aka the magnitude of the vector, and the direction is given in terms of the magnitudes of its component vectors, which we'll discuss shortly. This vector can be the position of a ball on a football field, or even the position of planets orbiting around the Sun. In any case, vectors are used almost everywhere in physics, and it isn't just limited to position. The same can be done with other quantities such as velocity, where the axis now represents speeds in the x and y directions, or acceleration, where its components in the x and y directions are also given in this axis form. So now that we're on the same page as to the concept of a vector, we need to represent it with some neat notation. So let's start with the simple position vector, which we are going to denote by r with a little arrow above it. There are a number of ways to express vectors in physics. Some use arrows above the letter, others use lines, and some just make the letter bold. But we'll be sticking with the arrow to remind you it has direction, and I personally think it looks the best. So let's consider the Cartesian coordinate system, where every position vector has 2 components, the x component and the y component. The components of a coordinate system basically tell us how to get from the origin of the vector to the end of the vector using some building blocks, which we are going to call unit vectors, unit meaning length equal to 1. In Cartesian coordinates, we use the x and y unit vectors, or xyz in 3 dimensions, denoted by little hats above them, which is typical notation for unit vectors. Now that we have our building blocks, we can use them to reach the end of our arbitrary vector r by simply shrinking or stretching them and then adding the outcome together. This leads us to the notation used to describe r in this coordinate system, where r is equal to x, this is the magnitude of the x component, multiplied by the x unit vector, plus the magnitude of the y component, times the y unit vector. To simply show this, we just use the amount each unit vector is stretched between curved brackets, aka the magnitude of x and y, which is hopefully how you're used to seeing coordinates expressed. Consider, for example, our original arrow. We can describe the position it points to by first counting along the x-axis, which we can see here is 3 units along, and then the y-axis, which is 2 units up. The result is that the vector r points to the position 3, 2. The magnitude of r tells us the displacement from the origin, i.e. how far away this point 3, 2 is from the origin if we moved in a straight line from the origin to that point. In this case, we would use Pythagoras' theorem and find the displacement to be equal to square root of 13. There are other coordinate systems which can be more useful when dealing with certain types of problems, such as using polar coordinates, which can simply describe motion confined to a curve, or using spherical or even cylindrical coordinates to exploit certain symmetries in your problem. Whatever the case, the main point is that each system will express the same vector, in this case r, using the building blocks, aka unit vectors, of that system before adding them together for the final description. Each of them will have a separate component for each dimension of the coordinate space they reside in. In 2 dimensions, you will have 2 components, in this case x and y, and similarly in 3 dimensions, you will have 3 components, x, y, z. Now that we have our notation, we want to use this to define some basic operations to perform on our vectors. And in this case, we're going to talk about 3 different operations: vector addition, subtraction, and multiplication. The last of which is technically 2 operations, but we'll get to that. However, we're going to start off by talking about vector addition. Now, the concept behind vector addition is actually quite simple. We take 2 vectors, r and s. We say that these vectors are simply equal to the corresponding x component, y component, and z component of each vector. Now, this bracket notation is actually just shorthand for what we were talking about earlier, where each unit vector is multiplied by the corresponding scalar function associated with that component. But I think it's pretty clear that the bracket notation is a lot cleaner and a lot nicer to look at. Now we might ask ourselves, what happens when we add these 2 separate vectors together? Well, we get what's known as the resultant vector, and it turns out the resultant vector is simply the component-wise addition of the previous 2 vectors, where the x terms, the y terms, and finally the z terms are all added together to form the separate x, y, and z terms of the new vector. And this is similar to vector subtraction, except in this case it's obviously just the opposite, where each term is minused from each other. Now, lastly in this section, we need to discuss vector multiplication. And there's actually 2 ways to perform vector multiplication. The first of these is the dot product, which gives us a number. And secondly, we have the cross product, which produces a vector perpendicular to the 2 input vectors. So, starting with the dot product, if we take our 2 previous vectors, r and s, along with their x, y, and z components, then what we find is that the dot product between r and s is simply equal to rx times sx plus ry times sy plus rz times sc. Now, I hope you can see a bit of a pattern forming here, where the x, y, and z components are all grouped together when multiplied and then added together to give the single number. This is what's known as component-wise multiplication and then addition. The second way to multiply vectors is known as the cross product. But before we do that, we need to talk about the determinant. Now, this might seem a little left field, but trust me, it's going to make sense in a minute. So, starting with a 2x2 matrix, if you think back to your linear algebra classes, if we have a matrix here, which is made up of A, B, C, and D, then if we look at the left diagonal, which in this case is denoted by A multiplied by D, and then we look at the right diagonal, which is B multiplied by C, then the determinant of a 2x2 matrix is simply the left diagonal minus the right diagonal. Now we're going to move on and talk about the determinant of a 3x3 matrix, which is a mathematical tool we're going to use to calculate the cross product. In this case, the product of r cross s. Notice that the top row of this new matrix is comprised of unit vectors and the bottom 2 rows of our usual vectors r and s. To find the ith component, we simply find the 2x2 determinant of the components which are not underneath that unit vector. And this is the same for j, where we notice that we ignore the y components and we take the cross product rx_sc minus rz_sx. An important point to note here is that the j component in the cross product is negative, whereas the I and the k components are positive. And to find the kth component, we take the 2x2 matrix of whatever is not underneath the k component. In this case, rx_sy minus ry_sx. and this is the final result for your cross product. In this fourth point, we're going to talk about differentiation concepts, which comes up a lot of the time when two functions act on each other in some way. And the first of these we're going to talk about is the product rule, which comes up when two functions are multiplied by each other and we want to know how to differentiate the outcome of this. So let's look at two scalar functions, f of t and g of t, where t represents time, and the scalar function means that we get one number as an output. And we might ask ourselves, what do we get when we differentiate f and g multiplied by each other? And this comes up quite a lot in physics, and what we find is that we can group the outcomes into two different terms. We get f of t times g of t differentiated with respect to t, plus g of t times f differentiated with respect to t. And you'll notice in this kind of grouping that the f term appears twice. In the first section it appears in itself, and in the second section it appears differentiated. And this is the same for g, where it appears differentiated and then on its own. Now we need to talk about the quotient rule, which, as the name suggests, involves dividing one function by the other, where the bottom function isn't equal to 0, and then taking the derivative of that outcome, in this case the time derivative. And what we find is we get the bottom function multiplied by the top function's derivative. And this f dot notation is something that's used a lot in physics, where f dot of a function is equal to that function's time derivative. So just bear that in mind, and going back to the quotient rule, we see that we minus the top function times the time derivative, or the derivative in general, of the bottom function all over the bottom function squared. And now, this might be a little complicated, so a good little rhyme to remember this by is if we call the top function high and the bottom function low, then we get low d high minus high d low all over low squared. And this is how people that are just being introduced to this rule tend to learn it for the first time. And it's quite a good rule. And I would honestly suggest it if you're struggling to come up with a formula yourself. Now the final rule we're going to discuss is the chain rule. But before that, we need to discuss a certain topic in functions known as composite functions. And that's denoted by this circle that appears between the two functions f and g. And by definition, that's what the three lines indicate, this is when we have one function as the input of the other function. And going in the opposite direction, if g0f, this is by definition g with f of t as the input. This is known as composite functions. Instead of having the input t to each function, we have another function itself as the input. So building on top of this, we take our composite function and then we take the derivative of this function, and we find that this is equal to the derivative of the outside function with respect to the inside function multiplied by the derivative of the inside function with respect to the variable that that function depends on. And this is what's known as Leibniz notation. Now on to our final point, we're going to look at using the differentiating concepts we discussed in our last point on the vector operations we discussed in point 3, and we're going to differentiate vector addition, subtraction, scalar multiplication, the dot product, and the cross product. And these are the most common types of differentiating that you'll come up against. So, let's start with defining our two vectors r and s as we have previously. And what we're going to look at is the resultant vector again, which is r plus s, which is the component-wise addition of the individual input vectors. And now we might ask ourselves, what if we want to differentiate the resultant vector? I.e., what if we want to differentiate r plus s, assuming both are dependent on time with respect to t? Well, all it is just dr by dt plus ds by dt. And by the same token, the subtraction of these two vectors is just dr by dt minus ds by dt. Nothing more complicated than that, and hopefully that's giving you a sigh of relief. So now that we've covered vector addition and vector subtraction, the differentiating both of them, We ask ourselves, what happens if we have a vector r and we multiply it by a scalar function f of t? Well, all this gives us is each individual component of the original vector r is multiplied by the output of the scalar function. And this is simply because the output of a scalar function is just a number, and multiplying any vector by a number will multiply each individual component by that number. So this is all there actually is to the operation in itself, but we have to ask ourselves, what if we come up to a case where we want to differentiate the outcome of this scalar function multiplying the vector? Well, what we actually get is just the product rule, where we can see that the scalar function f is multiplied by the derivative of r with respect to t plus the derivative of f with respect to t multiplied by r. And we can see from the video below how reminiscent it is of the product rule from earlier, where instead of two scalar functions multiplying each other, we have a scalar multiplied by a vector. However, we can see from below that the form stays the same. This might not come as a surprise because we're just replacing a scalar function by a vector, which is a vector-valued function. However, what might come as a surprise to you is that if we have two time-dependent vectors and we take the dot product and then differentiate them with respect to time, well, what we get out is actually the product rule applying to the dot product, where we have r dot producted with ds by dt plus s dot product with dr by dt, where the dot in each case now represents the dot product and not multiplication. Now, one last interesting point is that if we have our two vectors and we take the cross product and then differentiate with respect to time, well, once again we get the product rule form out, but with the cross product in the middle. But there's an important caveat here. The terms have a specific order, in that the original r cross s, whatever vector's on the left, the outputs must also be on the left, and similarly with the right terms. So for the cross product, differentiating that order matters. Now if we compare the dot product and the cross product side by side, we see that the terms actually don't matter, the order at least, for the dot product, whereas it does matter for the cross product. And this is the important caveat that you need to remember. Finally, I want to finish off with a review of everything that we've spoken about in the previous parts of the video, covering all 5 major topics. We first discussed what a vector actually is and what it may physically represent. After this, we moved on to discussing the notation used to represent a vector that would commonly be seen in textbooks. Afterwards, we moved on to discuss the operations which we can perform on vectors. And taking a sidestep from this, we discussed differentiation concepts that could be used. And then finally, in the last point, we tied it all together by differentiating the vector concepts that we discussed in point 3. So finally, thanks very much for watching the video. If you have a second, please consider liking and subscribing, as I really want to make more of these videos, and that'll help me do it. So once again, thanks, and I hope this video has helped you, and I'll see you next time.